Okay, people, let's get started. So we were talking about conformal mappings, and we're going to study in detail one particular conformal mapping between these two sets. So the half space given by the set of complex numbers whose imaginary part is bigger than 0, and the disk, the unit disk, which is just a ball of radius 1 around 0. Yeah, and we started to do this a little bit. So these are the mappings we are going to study. And then G of Z. Okay, and they are examples of Mobius transforms or fractional linear transforms, which is a topic we will study quite a bit going forward. Okay, so what did we show last time? So we showed that if F sends the half space into the disk and G sends the disk into the half space, and they are indeed inverses to each other, so G composed with F is the identity. Yeah. Then from this, F is indeed mapping exactly the half space into the onto the disk. So it's a bijection onto the disk. I'm going to write it like this. Okay. And for the same reasons, G of the disk is the half space. So the half space and the disk are conformally equivalent via these mappings. Right? All right, so how should we show this? Well, we're first going to show that F is actually mapping to some stuff inside the disk. Okay, so the image of F is going to be contained inside the disk. Okay, so this is F of the half space. And then vice versa, we're going to show that, or not vice versa, but then going the other direction, we're going to show that G of the disk is inside the upper half space. And so that will show these two things. And then we'll show this, and then that's everything we need. So let's start by showing that this particular fact right here. So let me underline this, calls this thing star. We start with star. And we just look at the coefficients of our mapping. So if we look at F of Z, by definition it is this thing, I of Z over I plus Z, and Z is we're mapping from the upper half space. Here is I, and here is minus I. And the distance from Z to I, right, no matter what point we have in the upper half space, the distance from Z to I is going to be less than the distance from Z to minus I. Yeah, just a clear, geometrically true fact. Yeah. So when we take the absolute values of this thing, I don't need to rewrite anything. So this thing is less than or equal to 1, and therefore we are indeed mapping into the disk. Yeah? Cool. So that one was easy enough. So this establishes star. Okay, next guy. We want to show that the disk is being sent into the upper half place by our mapping G. It's a bit more complicated, but let's do it. So let's give that a name. Let's call that thing star star. So for star star, let's take Z Z inside belonging to the disk, and consider our mapping given by this thing. G of Z is I of 1 minus, let's call it W just to be consistent, over this thing, 1 plus W. And what we want is to show that it's in the upper half space, which means the imaginary part of this thing is positive. Yeah? So the imaginary part of this thing is positive, we're all set. So if we say this thing is like this, then what do we have? So we have I of U minus U plus IV, like this. No, that's wrong, minus IV, like this. And then this is this plus U plus IV. Let's multiply by the complex conjugate of this so that we just have a real number on the bottom. So let's have U plus 1 minus IV over U plus 1 minus IV. And then on the bottom, we're just going to get the absolute value of this complex number, right? Squared, right? Because Z bar is mod Z squared, right? So if we do that, what happens? So we are going to have I of this stuff here. Now let's do this in a smart way, because what we care about is the imaginary part. So okay, to avoid rewriting too much stuff, let's just call this thing star, star, star. So from star, 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 the imaginary part of G of Z is going to be the imaginary part of this thing here. The bottom is just going to be a real number. So we want to extract the imaginary part of the top thing here, right? And so what does that mean? So that means we want to extract the real part when we multiply these complex numbers together. Yeah? Because the bottom's going to be real, right? So if we extract the real part when we multiply these complex numbers together, that will be the imaginary part of this. Yeah? You see what I mean? So on the bottom, we have just the absolute value of this thing squared. So it's 1 plus U squared plus V squared. And then we extract the real part of this. So we're going to have the real part times the real part. So it'll be 1 minus U, 1 plus U. And then the imaginary part times the imaginary part. Yeah? Yeah? So we're going to have this thing times this thing. So it's going to be minus V squared. Okay? And that thing is the imaginary part of the overall expression. Yeah? That thing is this thing. So the imaginary part of the thing in the blue box is this thing down here. Everybody happy with this? Cool. All right, so then we can clean up the expression. So then this is the difference of 2 squares. So this is 1 minus U squared, and now we have minus V squared. And on the bottom, we have this thing. Do I want to mess around with that thing? Yeah, I mean, I don't care about this thing, so I'm just leaving it as it is, because all I need is that this is positive, and I do see that it is positive because the bottom is just some positive number, right, because of squaring stuff. And this thing right here is positive because our original W is inside the disk, so the absolute value of W is less than 1, so U squared plus V squared is less than 1, so this thing is indeed positive. Yep. Cool. All right, so that shows exactly this thing that we wanted to show, that we're mapping from the disk into this half space. So it shows star, star. Cool. So we've got this, we've got this. So once we establish this, then we've got everything we need that F is a conformal mapping, exactly taking the half space onto the disk. And the same for G, it's sending the disk onto the half space. So let's just compose these mappings. Good to do this in the right order. Let's do it F composed with G. So F composed with G of W, that is going to be I minus G of W, I plus G of W, like this. And that's a complicated expression, but let's do it. So that's I minus okay, the obvious thing is to multiply top and bottom by 1 plus W. So we're going to have I of 1 plus W minus I of 1 minus W, like this. And then we're going to have I of 1 plus W, and then we're going to have plus I of 1 minus W. And then let's see what cancellations we have. So we're going to have the i's will cancel on the top, and we're going to have an IW plus another IW. So we're going to have 2 IW here on the top. On the bottom, we are going to have the i's will add, we'll have just 2i here, and then this IW cancels with this minus IW from here. So that is all we get at the bottom, and sure enough, that is W. So these things are inverses to each other. Yeah? Cool. All right, so we've established everything. And indeed, we have that these things are conformally mapping these completely different sets, a circle, onto a half space and back. Okay? And let's erase the board. I'm going to look at this even more closely. Okay, let's put up our mappings again. So we have f of z is this I minus z over I plus z, and this g of w, let's call it w, is equal to I of 1 minus w, 1 plus w, like this. Okay, so f is sending into the disk, so it's sending this thing into a wall centered around 0. Yeah? And it's doing this in a bijective way, so we'd expect the boundary to be mapped to the boundary, right? Yeah? Yeah? So let's see what happens. Let's take any real number, which is the boundary of this half space here. So let x belong into the real numbers. And then let's look at what happens when we do this. And as typical, when we have something like this, a nice thing to do is to make the bottom just a real number so that we see the structure more easy, sort of to multiply this by the conjugate. So let's multiply it by x minus I over x minus I like this. And then the bottom is just going to become 1 plus x squared like this. And as we multiply the top, what we get, let's extract the real part. So we're going to have a minus x squared. And then we're going to have a minus I, so it's going to be a plus 1. Right? So it's minus I times I, so that's plus 1. And then the imaginary part, what we're going to have, we are going to have a plus xi and another. So we're going to have 2xi here. Right? And let's break up this into the real and imaginary parts. So let's write this as 1 minus x squared over 1 plus x squared, and let's write this as x over I 1 plus x squared. Okay, yeah. This is good. All right, so let's think about what happens. So we're on the real line right here. Yeah. So if we start at 0, where are we sending 0 with this mapping f? So 0 is being sent to 1. So this is, we're sending the disk on 0, right? So 1 is right here. This is 1. So 0 is being sent to 1. Okay. Now, let's go forward with positive real numbers towards infinity. Yeah? So what is happening as we take some x, which is positive here, and we map it with this thing? What do you see happening? Let's imagine x is very, very big. If x is very, very big, if x tends towards positive infinity, what is happening here? So we write down what we know. So we know that f of 0 is equal to 1. What about the limit as x tends to positive infinity, f of x? What is that tending towards? Someone else. Just look at the expression here. You're just taking a limit, right? Louder. Say it again. -1, yeah? This is just -1 because as x tends to infinity, the limit of this thing is just going to be -1. As x tends to infinity, this thing just vanishes, yeah? Yeah? So if we look at what is happening, so let's say this is like, it's hard to express this. Say this thing is like infinity over here, and infinity is being mapped to -1 here, right? Yeah. And as we let x increase, right? So at 0, it's just 1. As we let it increase, then what is happening to this expression? It is going to decrease, right? It's going to ultimately hit 0, and then it's going to get negative, yeah? And it's going to get more and more close to -1 as this dominant thing on top and bottom will be this x squared top and bottom. Yeah? Yeah? So we see that, imagine the path of x as we move along. We start here, right? Yeah? And we are decreasing, ultimately becoming negative, and ultimately ending at -1. Yeah? Yeah? So we're going in a steady way this direction. Yeah? Yeah? And what's happening to this thing as we let x increase? Yeah? Well, as we let x increase, well, it starts off at 0, right? As we let x increase, this thing becomes positive. Yeah, becomes positive. It's going to get positive, more and more positive. But as we keep increasing x, then the bottom thing will start to dominate the top thing, and it will start to decrease, right? This expression will decrease, right? Yeah. So the imaginary part will start at 0, will increase, and then decrease. And as we go towards infinity, it decreases all the way down to 0. Yeah. Yeah? So what we see is that the path that x takes as it goes from 0 to infinity is indeed tracing around here, the upper half of this circle, ending around here. Yeah? We can just see it from the formulae. So this is what happens as we go along from 0 towards infinity. We are tracing around the upper half of the circle like this. Like this, yeah? Cool. And we do the same thing as we go from 0 to negative infinity. So we start with 0 at 1, right? And as we go to negative infinity, what's the limit of this thing? What's the limit as x goes to negative infinity? What's this? Someone else. What is this? Yeah, it's also -1, right? Again, because this thing vanishes and this thing doesn't notice if you're positive or negative, so this limit is just going to be -1 again, right? Cool. So if we look more closely what happens to the coordinates, well, as x goes from 0 towards negative, this thing is decreasing, right? This thing's decreasing initially, yeah? Until x gets large enough and the bottom starts to dominate the top, and then it starts to increase again, and ultimately as we go towards negative infinity, this thing will vanish, yeah? So the I coordinate starts by going down and then starts to go up again, yeah? And this coordinate, as x goes towards negative infinity, this thing steadily decreases as well because it's x squared. So as whether we go to positive or negative infinity, it's not going to change this in any way. It's still going to gradually decrease as x increases, and ultimately it's going to tend to -1. Cool. So as we go in this direction, then we are tracing around this thing, like this. Yeah? And just to emphasize it, this is where we are sending f of infinity. And if we think a little bit more about it, this guy is indeed just a meromorphic function, right? It's a meromorphic function. Yeah? In fact, it's a meromorphic function on the extended complex plane because we have a removable singularity at infinity. Yeah? We have a removable singularity at infinity, and that removable singularity is just the value -1. Yeah? So infinity has a unique value. Yeah? We have a unique value of infinity for f of infinity. Therefore, it's meaningful to treat this as a point on the extended complex plane, and that point is being sent to -1. Yeah? Cool. So, what is this thing doing? This thing is in a. I mean, the fact that this exists is kind of surprising, because this is doing all of this weird stuff in an angle-preserving way. So, if we drew some grid lines like this, like going off to infinity, like this, then the image of these grid lines, obviously they're very different. They are no longer going straight lines, but at all of these intersection points, they will all cross at 90 degrees because these angles will be preserved, right? So what is this thing doing? It's kind of taking this thing and then wrapping it all around, like it's taking the half space and kind of wrapping it all around into a circle, yeah. Onto a circle onto its side. So when I'm doing this, then also imagine me doing this. Yeah, yeah. Which is I mean, there's lots of software packages that show examples of conformal mappings, but yeah, but it's hard to draw. So it's kind of like all of these grid lines are like getting finer and finer and finer and finer, like this, and yeah, I can't really draw it, but we're fitting all these this infinite collection of squares all inside this circle, and they're all bunching up like here, really, really small, you know? And we're managing to do this while preserving angles, yeah? Which is pretty strange. It's pretty extraordinary, you know? But these mappings actually exist. These mappings actually exist. I mean, we've just seen them, right? They're not actually. It's not actually hard to show that this thing is angle preserving. We did this right at the start. Yeah. So, yeah, these are powerfully strange mappings. Okay, so it's an example of a Mobius transform, a linear fractional, also called a linear fractional transform. And we'll see more of this later. But a common theme, or a particular theme we should pay attention to, is that we are sending lines to lines are going to either be sent to circles or to lines. So in this case, this is a straight line being sent to a circle. We'll later learn that in general, a Mobius transform will send a line to either a circle or a line. That's something that will be a recurring theme for us. Okay, now let's talk about general conformal mappings. And in particular talk about Schwartz's theorem, or Schwartz's lemma. Let me try and spell this right. I hope this is right. So Stein calls this a lemma. Okay, suppose f is mapping the unit disk into the unit disk, and we have that f of 0 is equal to 0. Then we have a bunch of consequences. firstly, and this is the most important one, f of z is less than equal to mod z for any z inside the disk, and if f of z absolute value equals mod f of z, then f is linear. I.e., f of z is just equal to some complex number of mod 1 times z. Okay. Second consequence. Oh, I should have said for z not equal to 0, because it's certainly true at 0. Second consequence is that f prime of 0 is less than equal to 1, and again, if the absolute value of f prime is equal to 1, then f is linear. Okay, so proof. So we have unit disk being mapped onto the unit disk with the center being sent to the center. Okay. And what this theorem says is that this is an incredibly restrictive condition for these mappings. So that means that, this condition means that whenever we take a mapping, I should emphasize this is into the unit disk, so we just know it's inside the unit disk in the image. We don't claim we're mapping the unit disk onto the unit disk. So whenever we take any ball inside this thing, then the image of this thing, if this thing is radius r, then the image is contained within something of radius less than r. Yeah? For example, can you think of mappings that satisfy these conditions? What mappings satisfy these conditions? So, example, f of z equals z to the n. For sure, the unit disk is mapped to something inside the unit disk, in this case actually onto the unit disk. Yeah? And it also clearly satisfies these properties, right? Yeah. So if we take anything which has got radius less than r, then its image is something contained in a ball even with radius even smaller than r. Yeah. Yeah. And the only way if we take a ball of something less, a ball of radius r, and we have a point on it mapped to something which has got distance r away from 0, the only example of that would be as if we just have n equals 1. Yeah? And therefore it's a linear mapping. Yeah? Well, linear mapping is actually just a rotation with mod a equals to 1. All right. So what this thing says is that if we are mapping from the disk inside the disk, or with 0, sent to 0, then it's kind of contracting space at all scales. It's contracting space at all scales. So no matter what radius r you take around 0, it's going to squash down that thing. And that's kind of surprising. Again, it's completely not true if you don't have holomorphic mappings. It's easy to construct things that don't behave like this. This is not a lot of information to have on the hypotheses, but holomorphic mappings are so rigid that this is actually true and not hard to prove. Proof. Let's take the Taylor expansion of f. So take Taylor of f of z. So it's the sum from k equals 0 to infinity, ak z to the k. Since it's holomorphic inside the disk, then this radius convergence is at least up to the disk. Yeah. So this representation is true for mod z less than 1. And tell me something we know about this thing straight away. What we know straight away about the Theta series. Yeah. And since f of 0 is just a0, which is equal to 0. So actually, we have that f of z is equal to the sum as k is equal to 1 to infinity of ak z to the k. Yeah? Which in particular means that we can just factor a z out like this. Z to the k minus 1, yeah? And then so, we can have f of z over z is this thing, the sum from k is equal to 1 to infinity ak z to the k minus 1, yeah? And again, this will converge inside the unit disk, yeah? Cool. So we have that this function, f of z over z, is a nicely holomorphic function, yeah? It's a nicely holomorphic function, yeah? Cool. All right. Look at this. What nice information do we also know about f of z over z? And it's obvious we're going in that direction because we're trying to prove something like this. So what nice information do we see about f of z over z? I'm going to erase the board, think about it, and think about the cool stuff that we've proved. We have that f of z over z is this thing. It's the sum from k equals 1 to infinity ak z to the k minus 1. And this is true for z inside. Let's write the disk since we've introduced this notation. Yeah? Okay, so easy things to note is that, strictly speaking, f of z over z is not defined at 0, but it's clearly a removable singularity because by this representation for small z, it's very much like this coefficient a1 and it's bounded, therefore it's removable. And we can remove it by sticking in just the value a1 at 0. Yeah? So we can treat this thing just like a holomorphic mapping, yeah? With representation given by this. Yeah? In fact, this thing is basically for free saying everything I just said. Yeah? Cool. So this guy is a holomorphic mapping. What we want, we want to show that f of z over mod z is less than or equal to 1 all the time. Yeah? Yeah? Yeah. So that's the same as saying that the image of this guy is going to be contained inside the unit ball. Yeah? So this mapping is defined on the disk, and we want to show that its image is contained within the disk as well. Yeah? So let me do this as the disk. We want to show that this is true. Yeah? And I draw it like it's strictly contained. It doesn't, of course, have to be strictly contained, but we do need it to be contained. Yeah? It's really awful the way I wrote that. Let me get rid of that. All right. What tool do we know could help us with this? So here is 0. We want to show that this thing isn't too far out from 0. What tool is useful for that? Generally, if we have a holomorphic mapping, I spelled generally. I think that's just one R. If we have G from some domain into the complex numbers, where do we find Z such that G of Z is the supremum of all of these guys? Is it 0? Right, so this is for a general. This is just for a general holomorphic mapping some region into the complex plane. Yeah, So it's mapped onto this thing. Yeah. So where are we going to find the z that maximizes the distance away from 0? So suppose 0 is here. So there is some definite distance here that maximizes away from 0. Yeah? Because it's holomorphic, it's continuous. The image is a bounded thing if our original thing is bounded. Yeah? So where do we find it? Could z0 be here? On the boundary, right? Tell me why it can't be in the interior. Why can't we have z0 be somewhere here and then this thing here is g of z0? Why is that impossible? Why is that impossible? Give you a hint. Let's draw a little ball around here. The open mapping theorem. Yeah. So the image has to be an open set, right? Yeah. Yeah. Has to be an open set. Yeah. So we can't have that this guy is on the boundary, because then there would be some little open neighborhood around it where we could make it a little bit bigger, right? Yeah. So indeed, there is no z0 inside our domain that maximizes this. It has to occur on the boundary somewhere. Okay, cool. All right, so why is that useful in this thing here? We're trying to show that the image of this thing is contained inside the disk. Yeah? Yeah? And what we have to really care about is what happens to this thing near the boundary. Yeah? On the boundary. So let's take some r between 0 and 1 with r very near 1. Okay? So then consider this thing. Consider f of z over z on Vr of 0. Let's consider this thing. Yeah? And we know that if we try to find the guy mapping the smaller Br of 0, we're trying to find the guy that is taking it furthest away from 0, that thing has to be achieved on the boundary somewhere. Yeah? Has to be achieved on the boundary somewhere. Yeah? So take z0 such that f of z0 over z0 is equal to the supremum over the ball of radius r around 0 of this stuff. Yeah? Yeah? Cool. All right, so by maximum principle, z0 hold on. We do. Thank you, yes. This thing has to belong to the boundary around 0. Yeah? And why is that cool? Why is that useful for us? Look at this expression here. This expression. This is a hint. Yeah? Now what? Yeah? why did that make me happy? What can I do from here? What bound do I have now? Say it louder. Well, before we do that, tell me what bound I have. I want to make some explicit bound, right? I want to put some explicit bound. What explicit bound do I have from here? If I have any, do I have anything here I can put? What information do we have from the hypotheses? So the hypothesis was that f of 0 is 0, and the hypothesis was that, the mod of f of z is never bounded by 1. Yeah? Jaime's doing a lot of the answering. Let's other people get involved. I want you all to give me your feedback. Okay. Cool. All right. So this is some explicit bound for our function, but not quite in the entire disk, in something a bit smaller. Yeah? Yeah? Because this guy has to be achieved on the boundary, and on the boundary we have this thing. Yeah? So the supremum over the ball of radius r around 0 of our thing is less than 1 over r. And we're taking r to be very close to 1. Yeah? So it's not quite what we want, but very nearly, right? Very nearly. Yeah? So we've shown that if we are slightly inside with this ball of radius r, then this expression we're trying to control, f of z over z, is bounded by 1 over r. And r is a bit less than 1, so this is a bit bigger than 1. But the natural thing now is just to let r tend to 1, and then that'll give us exactly what we want, right? So letting r tend to 1, this gives us the supremum, this thing. Why did I have to do this stuff with the taking some r a bit less than 1? Why did I bother with this? Why couldn't I have just directly done this on a ball of radius 1? Perfect. F is not defined outside of the ball, right? So there's no meaning to picking some specific value on the boundary. It just doesn't mean anything. Yeah? The actual statement of the maximum principle is that the maximum is not achieved on the interior if you happen to have something which is also defined in the boundary. Therefore, corollary is it's achieved on the boundary, the maximum. Yeah? Cool. So I now have this. Now let's backward engineer what would happen if we actually had an equality. Right? If we actually had an equality. Yeah? So suppose for some, I should have probably said that better, z0 inside this unit disk, we have that f of z0 over z0 absolute value is equal to 1. Yeah? That would contradict the maximum principle unless... So the maximum principle followed from the open mapping theorem, which is true unless open mapping theorem says that the image under a holomorphic map, unless it's a constant, right? Because the constant functions are perfectly good holomorphic mapping, but its image is just an individual point, right? Which is clearly not open, right? So the open mapping theorem is for a non-trivial holomorphic mapping. The maximum principle is for a non-trivial holomorphic mapping. And if you have something that contradicts it, then that thing has to just be just a constant mapping, right? Yeah. So then by maximum principle, we have that this mapping f of z over z is just a constant, all z, and by this thing, the constant is just got norm 1, i.e. f of z is equal to c times z. It's a linear mapping with a coefficient of norm 1. In other words, just a rotation. It's just a rotation. Yeah? Cool. All right. So that is almost the full statement. Final. We need to establish that f prime of 0 is less than or equal to 1, and if f prime of 0 equals 1, then f of z is equal to c times z mod c is equal to 1. All right, so help me with that. How can we show that? Yep. Perfect. Yep. And since f of 0 is 0, right? Then this is equal to the limit, the limit as z goes to 0 of just f of z over z, and we've already established that this thing is less than or equal to 1, right? So just by the fact that this is a holomorphic thing and therefore it's continuous, right? So f of 0, the absolute value is a continuous function, right? Is this thing, the limit as z goes to 0, f of z over z, which is less than or equal, which is equal to the limit as z goes to 0 of this thing, because absolute value is continuous, and this is a continuous function, so this thing is just less than or equal to 1. I actually don't even need that, I just need that this is less than or equal to 1. So we're all good. Yeah? Cool. So that's definitely true. And if we have that, this thing is equal to 1, then that would mean that the absolute value of the limit as z goes to 0 of f of z over z is equal to 1, right? But f of z over z is a holomorphic function, right? And it has some value at 0, yeah? And that value would therefore be equal to 1. Its absolute value would be equal to 1, right? Yeah? So f of z over z at z equals 1, sorry, z equals 0, if I said 1 I meant 0, is such that has absolute value equal to 1, right? Yeah? Which again contradicts the maximum principle unless it's constant. Because again, f of z over z, even though I can't easily stick in the value 0 into this, it is a holomorphic function because we've seen the singularity at 0 is removable. Which max principle. Unless f of z over z is just equal to a constant and mod c is equal to 1, and we have exactly what we need. Yeah? Perfect. All right, so we have the full statement. And there are fairly frequently prelim exams that are tricky questions unless you remember Schwartz's lemma. So it's an easy thing to forget. It's kind of counterintuitive, but I'll try and find questions to test you using this thing, because in certain kind of questions, it's very, very useful to have this inequality. And if you don't remember it, then you just won't be able to do it with any of the other stuff that we've got in play. Okay, cool. So there's more to say about general conformal mappings, and we'll get to it if we have enough time. But what I really want to do now is to start to talk about Mobius transforms, because I think literally every prelim exam has a Mobius transform question, as you've probably seen if you've looked at these exams. So these questions can be quite tricky. It's possible to cook up some really tricky question involving you constructing a Mobius transform, constructing a Mobius transform, or identifying what a Mobius transform is actually doing. They are weird objects, Mobius transforms, and there's a certain skill to be able to answer these questions that you only get through practice. It's a little bit kind of disjoint from everything else we're doing, because it's more like a kind of branch of geometry, what we're about to do with Mobius transforms, where there's a different notion of reflection and different notion of symmetry, and with these different notions we can answer a bunch of specific questions, and that's what we're going to learn. So so this section is maybe a little bit disjointed. It doesn't depend on almost anything that we've learned so far. It's almost sort of independent, just little subtopic by itself, but a surprisingly rich topic, this particular class of mappings. Okay, so we're going to launch into some of the basic things about Mobius transforms, and next class we'll get into some more specifics of it. So Mobius transforms. Also called fractional linear. And these are guys of the form M of z equals az plus b over cz plus d, where a, b, c, d, of course, are complex numbers, right? All right, so first observation. If c was equal to 0, then it's just linear, right? So just a linear map, which is pretty easy to understand, because all it's doing is shifting space, rotating space, and dilating space, yeah? Another thing to observe is that if we consider m of minus d over c, then on the bottom here we're going to get 0, so this is sent to infinity. Okay, so these guys, we can see that they are meromorphic functions, and they are defined at infinity, and they send things to infinity. So we let z go to infinity. We'll see that m of infinity is just equal to a over c. Okay. So in fact, these things, you can think about them as acting on the sphere by a stereographic projection. So they are bijections of the sphere, moving the sphere around in specific ways, right? And the first thing to note, or the first theorem, is that M, any Mobius transform M, is the composition of 3 mappings, 2 of which are linear, 1 of which is the inversion 1 over z. So two linear maps. I should say actually affine maps, strictly speaking. So in calculus, we call mappings AX plus B linear because the graph is a line, but they are better described as affine, which is a linear plus a constant. So two affine maps. And the mapping, let's call it I of Z, which is 1 over Z, like this. Okay? And this is what we are going to first figure out, first see. So proof. This will be helpful for us later, because what we're later going to show is that the image of a Mobius transform is either going to be the image of a circle or a line will either be a circle or line. And the fact that the image of a circle or a line under an affine map is a circle or line is trivial, right? Because again, the affine mapping is just shifting space to a new 0 point, dilating and rotating things. So if you do that to a circle or line, you still get a circle or line. What is interesting and maybe a bit surprising is that this thing, when you act on a circle or line, is again a circle or line. And the calculation to see why that's true is a bit harder. But nevertheless, it's easy to do it for this thing than to do it in general. So once we have this, we're going to be able to show that the image of a Mobius transform, the image of a circle or line is a circle or line just by studying this particular guy. And that's one of the main purposes of this decomposition. And it follows from this, it just follows from algebra. So claim that we can write AZ plus B over CZ plus D as this thing. BC minus AD over C squared Z plus D over C plus D over C. Okay, this is just an algebraic claim, right? This is either true or not, and we're just going to do algebraic moves to show that this is actually true. But once we do that, then I claim that we have what we want, because let's take a closer look. Our first linear mapping will be this guy. Let's call it L1 of Z. That does this. That sends things to Z plus D over C. That's linear, right? Our mapping I will send whatever we have inside it to 1 over it. So we're going to apply it to this thing. So if we have I of L1 of Z, then we're going to have 1 over Z plus D over C, right? And our final linear mapping, or our second linear mapping, will be the linear mapping that does this. It goes BC minus AD over C squared. This is just a complex number, multiplied by Z plus DC. This is, again, definitely a linear mapping. And if we now apply L2 to this thing here, L2 of I of L1 of Z, then it gives us exactly this expression right here. Yeah? So, assuming we can prove this equation right here, then the statement we want is exactly following from it. Yeah? So it just comes down to doing some algebra to reduce this thing to this thing. Yeah? Cool. So let's do that on a new board. To do algebra on this expression, C minus AD over C squared Z plus D C plus, then we get some cancellations. We get this AD gets killed with this AD, so we have BC plus ACZ, and then sure enough we have, let's factor out the C. We have CZ plus D, and then yeah, we kill the C top and bottom, so then we have AZ plus b over cz plus d, exactly as we wanted. So this is the Mobius. Thank you for your help with this. Yeah? Cool. So this algebraic fact is indeed true. And we have the quaternary that we can compose any Mobius transform with one linear mapping, the inversion, and another linear mapping, right? And the linear mappings are easy things to understand geometrically. So the heart of the Mobius transform, at least the thing that is making it doing something non-trivial or at least dramatic, is this 1 over z part, right? Yeah. So you should really think of Mobius transform as something like this. It's just transforming space in a nice linear affine way. Then it's doing this inversion 1 over z, and then it's transforming it again. Yeah. Cool. So, you've got a few minutes. All right. So, next theorem. See how far we get with this. And this is a bracket I have here. Let's make a bracket better. So, theorem. Mobius transforms send lines or circles to lines or circles. Okay, so we're going to start just by proving that circles are sent to lines or circles. Okay. All right, and again, all we need to do is to show that 1 over z sends a circle to a line or a circle. Yeah? So enough to consider. M of z is just very simple. Mobius transform like this, and we start with a circle. So if we have a circle, what is it? And it's z minus a squared is equal to r squared, right? And we can write this as z minus a complex conjugate is r squared, and let's rewrite this as z bar, and then we're going to have a minus a z bar, and then we're going to have a minus a bar z, and then we're going to have just plus the absolute value of a squared, like this, is equal to r squared. Yeah? Just expanding out this thing. So let's put this a squared on the other side, and maybe let's write this like this. And then we have a z bar minus a bar z is equal to r squared minus a squared, like this. Yeah? I should say, let's first assume, well, okay, here we have a choice. We have 0 here, we have a here, right? And the radius is something. Now, if the radius is the same as the absolute value of a, then our circle is going to go through 0. Yeah? And then when we have this expression over here, then the right-hand side is 0. Yeah? Yeah? And if the right-hand side is 0, okay, yeah, it's trivially linear mapping. So if the right-hand side is 0, so if r equals absolute value of this, then what is this thing? Then this thing is, let's call this thing star. Is equal to mod z squared minus this thing equals 0. And let's divide everything by mod z squared. So then we have a minus a mod z over mod z squared. I'm running out of time, I guess. A z over mod z squared is equal to 0. And what is this thing? So let's think about what this thing is. This is the same as minus a of mod z over mod z times z. And this is the same as, I'm missing a complex conjugate right here. Right, so this guy and this guy doesn't. I'm miswriting this. There's no complex conjugate here, but this one here. Okay. So then this thing is this, and then this thing is this. Right? Equals 0, and then we do some cancellations, and we have that minus a over z minus a bar over z bar is equal to 0. Yeah. And then what's this? This is minus a, and this is our Mobius transform m of z, right? Minus a bar, and then this is m of z bar equals 0. Yeah. And what we're looking at here is a linear mapping. Yeah, this is a linear mapping. So the image of m of z satisfies this linear equation. Should have said that better. This is a linear equation. The image of m of z satisfies this. Yeah. So minus a w minus a bar w bar equals 0. If you write this out in terms of x plus iy for this w, what you're looking at is a linear equation in x and y. Yeah. So this is a linear equation in x and y. Yeah. So do you want to see this? So w is x plus iy. So then if we do this complex multiplication of this coefficient and this coefficient, yeah, what we're going to have is some expression, first order expression in terms of x, some first order expression in terms of y equals 0. Yeah. Which is exactly saying we have a linear equation. So this thing is just a linear equation, and therefore what we have is that the image of this thing satisfies the linear equation, therefore it is a line. Huh? So m of our circle, let's call the circle C. Yeah. Cool. And a posteriori, this is what we would expect, because if we have a circle going through 0, then as we know, 1 over z maps 0 to infinity, right? Yeah. So it should be something that includes infinity, and any circle won't include infinity, right? Yeah. So a posteriori, assuming the theorem is correct, then it's natural that if we have a circle centered on A whose radius is equal to exactly the absolute value of A, therefore it goes through 0, then that thing should be mapped onto a line. Yeah, so we've seen that it is a line, and that's what the only thing it can be. It can't possibly be mapped to a circle. Yeah? And if we look back at where we had this, it's because at this point we had the right-hand side was 0 in this particular case. Yeah? Cool. And if the right-hand side is not equal to 0, then this equation doesn't reduce down to something that we can just rewrite as a line after we divide through by absolute value of z squared. Yeah? And what we'll see next time is that when we have the right-hand side is non-zero, we're going to divide through by the absolute value of z squared. And this time we're going to get something that after we unwrap it will actually form a circle equation for this m of z. Okay, it's going to follow from the algebra again. So that will establish that the image of a circle will either be a line or a circle, And we'll know exactly when that will happen. It'll happen, the image will be a line when the circle goes through 0. Otherwise, it will be a circle because this right-hand side will be non-zero. Cool. All right. Bye-bye, people.